Hello AP Stats students, this is Mr. Liao and this is section 4.1 Transforming Relationships. What this section is basically taking a relationship that shows a curved scatter plot and making it into something linear so you can run linear regression procedures on it. And it is very unlikely to show up on the AP test, especially this year in 2020. However, it is part of one of the units that could be on the AP test, so I'm covering it. If this is really confusing and there are logs and there are other mathematical things, don't sweat it. It is really unlikely to show up. Okay, but I'm going to go over it anyway. I'm going to go over basically pages 14,4-9 all the way to page 4-16. I'm cutting out some stuff. I'm going to go through some of it fast, and at the very end, you'll see the summary. You will need a calculator, and you're going to basically take the log of x and y and see which relationship converts a curved relationship to a linear relationship. So we're going to look at why transformations are sometimes necessary to make our data linear. We're going to apply logs to some curved patterns to make them linear, and then we're going to find the least squares regression line and make predictions using an exponential and later a power model to transform data. So one of the examples is body weight versus brain weight. I'm skipping the first picture. We have 92 data points, and you can see there's a curved relationship, and that just tells you that the linear relationship is not the best model for predicting for relating two variables, birth weight and body weight of mammals. So I'm skipping a lot of the stuff here. Notice if you were to take the log of both the x and the y variables, the log of the brain weight, which is the y-axis, and the log of the body weight, which is the x-axis, now you will see that the 96 mammals form a very, very strong linear relationship. In fact, the R is 0.96. So transforming data, applying a function such as a logarithm or a square root to quantitative transforming variable is called transforming or re-expressing the data. Simply converting units doesn't change the shape of the plot. If you remember one of the things we did in chapter 1, if you change the conversion, if you convert something, it doesn't change the shape. Linear transformations cannot straighten a curved relationship between two variables. Now the goal of transformations, by the way, if I'm going too fast, you're welcome to just stop and pause the video at any time. We want to find a linear relationship between y and some function of x so we can fit a least squares line to the transformed data so that we can do linear regression on the transformed data. That is the goal of transformations. So I'm skipping the first part of power transformations. We're moving on to types of transformations. We can transform one or more variables by transforming one or both of the variables. So here's some examples. Taking the log of both or one of the variables. Raising one or both variables to a power. Taking the root of one variable. Taking the reciprocal of one or both variables. Now we're going to be focusing mainly on the first two types of transformations. We're going to discover that it's easier to take the log or the natural log of both sides to achieve linearity instead of trying to guess what the exponential relationship is, in other words, what the exponent is, or what the power relationship is. Is it cubic? Is it quadratic? Is it something else? Instead of trying to guess, it's easier to use logs or natural logs to find a curved relationship and turn it into something linear. So the two models we're looking at are the exponential model, where y hat equals a times b to the x. Notice that the x variable is the exponent. And the power model, where y hat equals a times x to the b. So x is the base of a constant exponent b. So that would be like a quadratic or a cubic relationship. So linear growth increases by a fixed amount in each equal time period. Linear growth is an additive process. Exponential growth increases by a fixed ratio or percentage of the previous total for each equal time period. Exponential growth is a multiplicative process. And I'm going to skip the example and move on to the next page. So in the exponential growth model, a and b are constants. In this model, the response y is multiplied by b in each time period to find the next y value. So to transform an exponential growth, let's see what happens. So this is the mathy part. You don't have to remember how to do this. I'm just showing you where it comes from. Let's take the log of both sides. So the log of y hat equals the log of the quantity a times b to the x. Now if you remember your laws of logs, if you have a product, that is equal to the sum of the logs. So log of y hat equals log a plus log b to the x. By the way, if you want to use natural log, you can. Our book tends to use log. So now let's use the other rule for logarithms. So for the second term on the right, log b to the x power, we can move the exponent to the front. So log of y hat equals log a plus x log b. Now if you look at this equation, log y hat equals log a plus log b times x, we have a line with the slope log b. If you were to take the log of y, you'll notice there's a linear relationship where the slope is log b. Okay, so it's basically a plus bx like we learned in chapter 3, but log of y hat is in a linear relationship with x with the slope of log b, which means if you take the log of y hat, there is a linear relationship for an exponential equation with x. Okay, it straightens the scatter plot of y against x. Log b becomes the slope of the straight line that links log y to x. So in summary, if the data is exponential, the graph of x comma log y will be linear. And the least squares regression line of x comma log y is log of y hat equals a plus b to the x. Okay, so what you're doing is instead of plotting x and y and doing linear regression on x and y, you're going to be doing linear regression on x comma log y. So you'll take all the y values, take the log of all those y values, and then do linear regression on x and that list of the log of y values. So I'm going to go through this quickly. You want to try to write this down unless you really stop. Considering thousands of bacteria in culture in a number of hours, so let's suppose you put these into list 1, list 2. You don't have to. Let's take a look at a scatter plot. Scatter plot shows a curved relationship. So this is using L1 as the x variable, L2 as the y variable, and you can see the curve. Now let's see if this is exponential growth, and you don't have to do this. I'm just going to show you. Let's suppose I copy L2 into L3, delete the first value in L3, then add any value at the end. What I'm doing is I'm taking 2.4, dividing it by 1.8, and that gets me 1.33. I will do the same with 3.1 divided by 2.4, and that gets me 1.29. So notice the ratios are basically what you're doing to each y value to get the next y value. And you notice that they're very, very close to about 1.3. Now, if you were to draw a scatter plot, instead of doing x and y, we now have a new list. This is log, and now in the notes I put L3. I'm going to use L4 just to be consistent. So L4 is you're going to take L2 and just save it into L4. So the log of L2 equals L4, or becomes L4. So all these values here on the right are the logs of column 2. So now we're going to do a scatter plot of x, which is hours, and log of y, which is the log of the number of bacteria. And you take a look at the scatter plot of L1 and L4. In other words, L1 is x, L4 is the log of y, and did the scatter plot of L1 versus L4. This is the scatter plot. It is a very strong linear relationship. Now let's do linreg on L1 and L4. So remember, linreg is under stat calc number 8, which is linreg, and you can store that into L1. Don't worry too much about the calculator mechanics. You don't really need to know. Here is the linear regression on x and log y. So notice that the r squared is 0.999. R is very, very close to 1. The residual plot shows random scatter, which tells you that now that we've converted the data or transformed the data using the exponential model, the linear model is a good fit. So if we write our linear regression equation, instead of using y hat equals a plus bx, we're going to use log y. So this is our equation. The log of y hat equals a plus bx. Remember, we did a scatter plot of x, which was in L1, and log of y hat, which is in L4. So instead of using y hat equals a plus bx, we're going to use the log of y hat equals a plus bx. So now we're going to put in the y variable, which is bacteria. The a value you can see from the linreg information in the box is negative 0.002, and the slope is b, which is 0.2545. So this is your regression equation. The log of y hat equals negative 0.002 plus 0.2545 times x, which is the number of hours. So the question is, how many bacteria do we predict are present after 3.75 hours? So instead of using y equals a plus bx, you're going to use log of y hat equals a plus bx. So we're going to plug in 3.75, and we'll see that the log of the number of bacteria is 0.9524. Now you're going to do the inverse operation of logs, which is the anti-log. It is 10 to the power of both sides. So 10 to the power of both sides tells you that there are about 8,960 bacteria after 3.75 hours. Now if you look at the chart on the previous page, you will see that the 3.75 fits very nicely to where the graph is. You're given 8 is 3.5, 8,000 bacteria after 3.5 hours, 10.6 after 4 hours. You see 8.96 slots in there very nicely. Now, an inverse transformation is basically taking the log of y hat equation and expressing it in terms of y hat. So to do that, we need to take the anti-log, or 10 to the power of both sides. So this was our exponential model equation. Log of y hat equals a plus bx. We take 10 to the power of both sides, we get y hat equals 10 to the a plus bx. So you have this exponent here. Now the rules of exponents say that if you have 10 to the a plus bx as the exponent, you can separate it out to 10 to the a times 10 to the b to the x. So this is the inversely transformed equation. We've taken this linear regression equation from linreg, but it was in log of y hat, and now we've expressed it in terms of y. Now notice we still have the form a times b to the x. The a is like 10 to the a, the b is 10 to the b. Both of those are constants, and to the x power, x is the exponent. So to convert this value to linear regression, take 10 to the power both sides, and you end up with y equals 10 to the negative 0.002 times 10 to the 0.2545 to the x, which comes out to this equation. Now again, you don't really have to worry about this too much. This is really unlikely to show up on the AP test, but I'm just covering it just in case it does show up. Now to use the calculator, because the exponent for 10 is so small, the calculator will return a 0. So what you're going to do, I'm going to just put the slides up. You can look at it later if you want. This is something you really don't need to know how to do. But basically, I'm putting y1 on the calculator. y2 is 10 to the power of y1, and then it just allows you to figure out the value by using a calculator. So you can use your calculator to predict how many bacteria will be present after 4.3 hours. It's fancy. You don't really need to do it this way. You can just plug in 4.3 into the regression equation. Log y hat equals a plus b to the x, b times x. So we predict there will be 12,370 bacteria after 4.3 hours. So in summary, for the exponential model, if the data is exponential, the data are exponential, the graph of x comma log y will be linear. And you would basically take the y values, take the log of all those y values and run linreg on x versus log y. So if a variable grows exponentially, its log will grow linearly. Now we're going to look at the power law model. So in the power law model, remember the x is the base of an exponent and the exponent itself is constant. So if you order pizza, it is measured by diameter. So you would think it's a quadratic relationship. It turns out the area of a pizza is pi over 4 times x squared, where x is the radius, x is the diameter. So this is the power law model. Notice x is the base. That's the variable. It changes, but the exponent itself is squared. If we were looking at volume, we would probably be looking at something x cubed. So in the power law model, a and b are constants. In this model, the response variable y is multiplied by x to the power of b each time to get the next y value. So to transform power models, again, we're going to do the same thing we do with exponential. We're going to take the log of both sides and see how it looks. So the log of y hat equals log of a times x to the b power. Again, using the law of logs, log of y hat equals log of a plus the log of x to the b power. Using the law of logs again, we get the log of y hat equals log of a plus b times the log of x. Now notice again we have another linear relationship, but this time the y variable is the log of y hat, and there's a linear relationship between the log of y and the log of x with a slope of b. So that means if you have a power relationship, a cubic, a quadratic, or some other relationship, a square root relationship, because the power will be 1/2, it means by taking the log of both variables, you would end up with a strong linear relationship, because you will see that there's a linear relationship between log x and log y. So the power b becomes the slope of the straight line that links log y to log x. So if we're quadratic, that means b would be 2. So the slope of the linear regression equation would be about 2. So in summary, the data has a power relationship, log x comma log y will be linear. Remember, with an exponential relationship, it was x comma log y was linear. So this is the log of both x and y graphed against each other. So looking at the body weight, here's the equation. It turns out it was a power relationship, so log of y hat equals 1.01 plus 0.72 log of x, where y hat is predicted brain size in grams and x is the body weight in kilograms. Now, the inverse transformation, again, is basically taking an equation expressed in the log of y hat and making it in terms of y hat. So to do that, again, we need to take 10 to the power of both sides. So you get y hat equals 10 to the a times 10 to the log x to the b. And notice 10 to the log x, those are inverse functions. So y hat ends up being 10 to the a times x to the b. So again, b was the slope of the regression equation, regressing log of y hat against the log of x. That also is the exponent in the power equation. So y hat equals 10 to the a times x to the b. Again, you probably don't have to worry about this on the AP test. I'm just telling you what it is, just in case it does show up. So looking at brain weight versus body weight, you're going to take 10 to the power both sides, and I'm just going to show you the quick math here. It ends up being 10.233 times x to the 0.72 power. So you can just follow the math along to see that. So now we're going to try to use the equation to make a prediction. Let's suppose we have a large Yeti-like animal with an estimated weight of 127 kilograms. We're going to try to estimate the size of Bigfoot's brain. So this is 10.233 times 127, which was the X value, the weight, to the 0.72 power. Put that all in, and you get about a 334.8 gram brain for Bigfoot. So again, this is a prediction. It's not conclusive. So in the example on the top of page 14, we have 20 fish listed by year and their length and their weight. And we're going to try to predict a relationship between the weight of a fish and its length. Now you would probably imagine it's cubic because length is one dimension and weight, like volume, is cubic. So we're going to expect something to be in a cubic relationship. So we're going to put, you don't have to do this, but the length's go into list 1, which is X. The weight's go into list 2, which is Y. Now, if you were to actually plot list 1 against list 2, X versus Y, so let me write down X, comma, Y, you would see that it's a curved relationship. Now, just because it's curved, you don't know right away whether it's exponential or power, and we'll get to that in a little bit. You just know you have to do something to it. So this is the relationship we expect to see. If you take the log of both sides, you will see that the log of weight we expect to be related to the log of length. So this is the log of Y hat, this is the log of X. So that's the relationship we expect. And it turns out if you take the log of X and put that into L3, you take the log of Y and put it into L4, you look at the scatter plot, you notice this is strongly linear. So this is a plot of log X comma log Y. So by basically taking the log of both X and Y and then redoing the scatter plot, you have a very strongly linear relationship. Now, if you decide to do the exponential model, which is X comma log Y, you will still see that it's curved. And so you know the exponential model couldn't possibly be right because it didn't straighten out the relationship between the two variables. So again, this is the graph of log X comma log Y. So if you were to do linear regression, and this is on L3, which is the log of X, and L4, which is the log of Y, those are the numbers you get. Here's the residual plot, pretty much random scatter. So you will see the equation is log of Y hat equals A plus B times the log of X. So here is the log of Y hat, which is the log of weight. The log of length is the log of X. So you put in A, which is negative 1.8994, the intercept. B is the slope, 3.0494. Notice it's very close to 3, which is what we expected. So the correlation of the logarithms of length and weight is 0.9993. So it's very strongly linear. Again, you can't say the original data is strongly linear, but you can say the transformed data has a very strong linear relationship. So now doing an inverse transformation, take 10 to the power both sides, and you see that the value of the predicted weight, Y hat, is equal to 10 to the A, which is 10 to the negative 1.9994, times X to the B. X is the length to the power of 3.0494. So notice the exponent is very close to 3. So now we're going to plot the power equation. We're going to use L3, which is log X, L4 log weight. So if you were to put this on your calculator, this is what it would look like. You don't really have to do this, so I'm just going to show you. If you want to look at it more closely on your own, you're welcome to do that. So this is, if you were to take the power equation, this is the original data, and remember it was curved, and you come up with a new equation. The regression equation is that curved line that's going, or that curve that's going through the original data. So you can see how strong the inversely transformed least squares line is to the original data. So what would be the predicted weight of a fish 36 centimeters long? You plug in 36 for X, and you see the predicted weight is about 702 grams. And if you want to use a calculator, this is what you would end up with. So a problem like this is how you would do these problems. You don't know if before you look at the problem if it's exponential or power. So what you're going to do is you're going to have to end up trying both. So here we have X is the distance from the sun, Y is the period of revolution Earth years for the 9 planets or the 8 planets plus Pluto. We want to know if Eris is considered a new planet based on this model. So we're going to look at 3 scatter plots. First, we're going to look at period versus distance, which is X and Y. Then we're going to look at exponential, which is the X log Y. So distance is X, and the log of period, which is Y. And then last is the power model, which is log X comma log Y. So this is the original data. So notice it doesn't look linear. This is plotting X and y. This is the exponential model. So I'm going to write exponential here. Notice that is log of period, which is the log of y, against distance. So I'm going to write down here just so you can see it. This is x comma log y. So exponential model, you will notice that there's still a curve, not linear. So the exponential model is not a good fit. Finally, we have the power model. So I'm going to write down power here. You will notice here that if you take log x comma log y, you now transform the data to form a strongly linear relationship. So we're going to use the power model to do the problem. So based on these three models, we have the original model, x comma y, then we have the exponential model, which is x comma log y, and then we have the power model, which is log x comma log y. Again, we see that the power model is the best of the three. That's the one we're going to go with. Now, there will be times where you'll see that exponential power look about the same, and mathematically, you can probably go with either one, it'll be fine. So let's find the least squares line. We're going to use L3 and L4, which is log x log y. Here's a linear equation. There's a residual plot. Now notice the residual plot does have a bit of a pattern. But what I also want you to notice is this number here. This is the highest value. Remember, this horizontal line is a residual 0. This number is 0.00028. So compared to the x and the y values, it is really small. So I wouldn't worry about it. Notice that the slope is about 1.5. So relative to 1.5, this is a very small residual. So even though the residual plot does have a pattern, the numbers are so minute that you wouldn't have to worry about it. Look at the r and the r squared. Very, 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 very strong, almost perfect linear relationship with the transformed data. So log of y hat equals a plus b times the log of. Here's computer output. We're not gonna worry. Here's the residual plot. Find the power equation by taking the 10 to the power of both sides. So 10 to the power of both sides, you end up with what you see here, 10 to the 0.0001105 times x to the 1.5. So let me just write it using the symbols. This is y hat equals 10 to the 0.0001105 times x to the 1.5 power. So here's the power equation if you were to plot it. Again, not something you have to worry about. To predict, what would be the predicted period of revolution for Eris, which is 102.15 astronomical units from the sun, and you just plug in 102.15 for x, and you see the period is about 1,032 years. So confirm your answer using the calculator. That's what it is. So here's the summary slide for transformations to achieve linearity. We have a curved scatter plot, so you can't use the linear model. What do? We have two possibilities. We have the exponential model, which is y equals a times b to the x. We have the power model, y equals a times x to the b. So if you were to take each x and y variable and take the log of both, if you were to take x and plot it against the log of y on a scatter plot and you see that it's linear, that is the exponential model. Here are the following formulas. You would use the linreg on x and log y. So log of y hat equals a plus b to the x, and you can see the inverse transformation expressed in y hat. If you were to graph log of x comma log of y scatter plot, and you would see that is a straight line linear relationship, that is the power model. So you're going to take the least squares regression line, run linreg on log of x comma log y. So your equation is log y hat equals a plus b times log of x, and you see the inverse transformation. Again, this is really unlikely to show up in the AP test. So if it does, it's covered. If you don't remember it, I wouldn't worry about it. That's it. Have a good day.